So last lecture we left off at decarboxylation, and the reason why the decarboxylation only occurs when you have a carboxylic acid beta to a carbonyl is because this transition state has to form, and it could only do that to make the six-member transition state when it's at the alpha beta, so 2 carbons over. Then the hydrogen bond. So this hydrogen on the carboxylic acid will hydrogen bond with that carbonyl. This is very stable, and with heat, the carbon dioxide, so this right here leaves as carbon dioxide, and you can see how the double bond forms with this carbon, and then that double bond, that 2 electron is moved over to form the enol, and then the double bond O grabs the hydrogen to form the OH. So this, as you know, enols are not as stable as the keto, or actually in this case the carboxylic acid form. So this enol of the carboxylic acid is not very stable, as shown by this arrow, in which most of it will be in this form. So notice the overall transformation is that this R was from the Rx of the alkyl halide, and you're adding CH2 and the carboxylic acid to the R group. And that's why this malonic ester synthesis is pretty useful, because it's a very easy way to put on 2 carbon long with the functional group onto an R group. All right, so this is like sort of a long process, and what you're seeing here is you are looking at like the whole reaction in a shorter form. So this is how it would look. You would start with the malonic ester. Sodium methoxide is the base. It's going to form an enolate here, and then you're going to react with an RX to put an R group here. And then if you want, you could also put another R group. So you could be R and then R prime. So you could use another equivalent of base to deprotonate the other proton, and then react it with another RX to dialkylate. And the R could be, you know, 2 different alkyl halides or same. All right. So then this right here condition is the decarboxylation and the hydrolysis. So this is hydrolysis, and then you heat it, and then you get the diacid, and then the diacid, one of them will decarboxylate, giving you 1 remaining carboxylic acid. All right. So this part came from malonic ester, and the R groups are from the alkyl halides. All right. So the other, so this is a drill that you should be able to do, and I expect you to do this reaction and tell me what the final product will be, and just, you know, follow this what we've gone over to tell me what the specific R group would look like, okay, in the final product. So the second is the acetoacetic ester synthesis, and it's very similar to malonic ester synthesis in that all you're doing is starting with acetoacetic ester. So this is acetoacetic ester, and this is very, very, very similar to the malonic ester synthesis. So it overall is you're taking RX and you're reacting with the acetic ester enolate, and what you're doing is, instead of putting in the acetic acid, you're putting this group. So it's like an acetone equivalent. Sorry. So notice it's 3 carbons long, and notice it sort of looks like acetone, which is CH3, double bond CH3, but enolate of acetone. So you're putting this group onto the R group of the alkyl halide, all right? So I'm not going to go over like in detail because it's very, very similar to malonic ester, but basically you're starting with acetoacetic ester, and this is base, as you know, sodium methoxide, and because this is once again pK of 9, because it's flanked by 2 carbonyls, you make an enolate here in between the 2 carbonyls. You react with the Rx, and once again you want the Rx to be primary alkyl halide if it's possible, and then you form this bond, and then if you want another R group, so this is optional, the 3rd and the 4th, so if you retreat it with another base, then you form the enolate again with the remaining hydrogen, and then you could put the other R group. So these are the 2 bonds that you make, and then this is hydrolysis again, and then this is minus CO2 decarboxylation reaction. Okay, so notice the difference between acetoacetic ester and the malonic ester. And the malonic ester is diester. Here, the acetoacetic ester is just ester on one side and a methyl group on the other side. So it's a ketone and an ester. So when you decarboxylate, after you hydrolyze to carboxylic acid, this is what's going to be removed. So what you have remaining is this part right here, the CH3 double bond O with the carbon with the R groups attached, and that would be the final product. All right. So this is just reiterating what I just talked about, that this is the equivalent that you're putting it on. And once again, this is a drill problem in which you're now starting with the acetoacetic ester and then base. So you should be able to draw the enolate here, which is going to be negative charge there. And then this is your Rx, all right? And then tell me what the product will be. And then here, the dilute NaOH and H3O plus is to so this is to saponify the esters, and then you get the carboxylic acid. So this is just deesterification step, and then this should be the decarboxylation step. So you should be able to give me what the product of that would be. And then this is basically same thing, another question. So this is one, and this is another question that you should be able to do. So when you see this right here, this is the hydrolysis under basic conditions. So obviously, as you know, you could do it under acidic or basic conditions, all right? So on top of that, you should be able to do 22.33, 22.35A, 22.39AB. And then the last thing I want to go over is this chemistry that you went over is not restricted to just 2 type of starting material, the acetoacetic ester and malonic ester, but you could have any carbon with 2 things that are attached to the carbon that are electron withdrawing groups. So it's denoted by Z and the Z prime. So any of these that is listed here could serve as the electron withdrawing group. So it doesn't have to be just carbonyls, as you saw here. You could have a nitri, you could have a nitro group, you could have a sulfonic derivatives as well. So all these things, when it's directly attached to C, and if you have 2 of those, it's going to make this carbon very, very prone to removing the proton. It'll be easy to use any kind of base to deprotonate and form the enolate. And then you could do the alkylation reactions as shown above, and then make a carbon-carbon bond. So this is very useful, versatile type of reactions. Okay. So the last thing, I have literally 2 minutes. The last thing I want to do is in your homework problem, you're told to do a lot of synthesis problems. So for example, here's one of them, and I just want to kind of go over the strategy for doing these problems. And so the two kinds of products that you're going to be asked to synthesize are going to be so here's another example. So here what you're recognizing is if you want to use a malonic ester, so notice this part could come from malonic ester. All right, so you have to recognize any carboxylic acid, if you have a CH2 next to it, it could be made from malonic ester synthesis, right? So so that means this group right here must have been my Rx, right? So if you draw that, that might help you to go back and then come up with the malonic ester that you need in order to get to there. So you know the malonic ester from your previous paper looks like this. So you have this, and then your first step will be to react with the base, and you don't need a LDA, although I can't mark it wrong if you wrote that because it will do the job, but you only need sodium ethoxide to deprotonate because these protons are more acidic. And then 2 would be your Rx, right? So then you will form this bond that's shown here, but then you would have all these things attached to it, right? So you're going to have to 3 do hydrolysis to remove the ester, and then 4 heat to decarboxylate, right? So it would be 1, 2, 3, 4 would give you this product that you desired. Okay, now the other kind of synthesis that you're going to be asked to do are basically ketone derivative, and it's going to be a methyl ketone. Notice that when you use acetoacetic ester, you're going to end up with a methyl ketone with this carbon is where the alkylations occur. So so notice we have 1R group and a 2R group, right? So let me just make it different so that you can see. So notice this is R and this is R prime. 2 alkyl groups are attached to this. You should be able to see the acetone equivalent right here. So whenever you have a methyl ketone, think of using acetoacetic ester synthesis. And then whenever you see carboxylic acid with a CH2 group, think of using malonic ester, right? So the acetone equivalent comes from the ethyl acetoacetate. So here's my CH3 and then CH2 group, and then so if you react it with sodium ethoxide, and then react with ethyl bromide, and then 3, running out of time, so I need to stop. But you see the sodium ethoxide, and then 4, there will be propyl bromide, and then you need to hydrolyze and then decarboxylate. All right.